Good morning, class, and welcome to this lesson on Geometric Optics 7, Total Internal Reflection. Today we will be able to describe when total internal reflection occurs with light. So let's define that first. Total internal reflection. Total internal reflection is when all incident light is reflected back into the medium. Okay, all incident light is reflected back into the medium. And you might say, well, isn't that just reflection? Isn't that just reflection? But we're not using a mirror. We're actually going from one medium to another, and all light is being reflected. So let me show you a picture here. In situation A, we have an incident ray, light's hitting the medium. Some of it's going to be reflected back. That's going to happen no matter what. So some's going to be reflected back, and then for the most part, it's going to be refracted out. And as you can see here, it's going from one medium that has a larger index of refraction than the other, a larger index of refraction, and it's bending away from the normal. Okay, this is what we talked about in our last video, and this is what we know as normal. Well, what if I change the angle of this to that? As you can see, the refracted way is going to keep bending away from normal. And if I keep moving this angle out, it's going to keep on getting closer and closer to the actual medium. And so as you can see here in picture B, we have something called a critical angle. A critical angle. And we define that as angle C, okay? Angle C. And the critical angle is when the angle of refraction equals 90 degrees. As you can see here, if we hit it at the best angle, the angle of refraction is going to be 90 degrees away from the normal. So it's going to actually bend right down the surface of the medium. So this is the critical angle right here, critical angle. And so what happens when we go past the critical angle? If we go past the critical angle, it's still going to bend away from the normal just like it did before, and we call this total internal reflection. And total internal reflection occurs if the angle of incidence is greater than the critical angle. This was the critical angle right here from this picture. That's the critical angle. The angle of incidence is greater. This angle right here is greater than this one. And when it hits the surface, it's going to be totally reflected back inside. Okay? So one more time, when the angle of incidence is greater than the critical angle. And so what we have here is if we take Snell's law, we have n1 sine theta 1 equals n2 sine theta 2. If we want to know the critical angle, so I'm kind of heading back to this picture right here. If we want to know the critical angle, if theta 2 is equal to 90, sine of 90 is just equal to 1. Is just equal to 1. So we have n1 sine theta 1 equals n2. And so if we want to know the critical angle, the sine of the critical angle is going to equal n2 over n1. And that's going to be the sine of the angle. And so it means the critical angle is going to equal the inverse sine of n2 over n1. So that's how we find the critical angle. Okay? And in these situations, n1 is going to be greater than n2. As you can see here, n1 is in water, the index of refraction in water versus the index of refraction in air. We know the index of refraction in water is greater than n2. It only works when this happens. And so it will never be the opposite. N1 will never be less than n2 to find the critical angle, okay, to find the critical angle. And so this phenomena kind of explains a few things. So diamonds sparkle, so I've heard. That's because they have a very small critical angle. They have a very small critical angle, and so light entering, it's very common for the light entering has a larger angle than the critical angle, and so light is reflected totally internally reflected inside the diamond, and so we get a sparkle feel. So we get a sparkle look to a diamond. So it is not magic, it is not love, it is not fairies, it is physics. Okay, so we have that is the reason why diamonds tend to sparkle. Okay, they have a very large index of refraction. The index of refraction for diamonds actually is diamond n is equal to 2.419. Very large number for index of refraction. It's also how fiber optics work. How can I send a light ray down a tube that's being bent all the time? It is because when we send a light ray into the tube, it is being totally internally reflected all the way down the light. And fiber optics are becoming so big nowadays is because they're so much more efficient. There's less friction, there's less heat. It's light going through a medium and with almost no loss at all. So this is how fiber optics worked as well. This is how we can send a light ray to the end of a tube without seeing it in the light, in the actual tube.